Hello everybody, and welcome to Unit 3 covering earthquakes. This section, Section 1, is going to cover earthquake basics. So we see here four different sort of plate boundaries. The first two up here would constitute convergent boundaries, splitting them into two parts here. A continental collision boundary, where you have a continent and another continent, which are converging, and a subduction zone boundary, where you have, in this case, continental and oceanic lithosphere, oceanic and continental plates where the ocean is subducting beneath the continent. We also have down here an example for divergent and transform boundaries. Notice that the orange are the shallow earthquakes and the blue are deeper earthquakes. We get only shallower earthquakes at the divergent boundary and at the transform fault boundary. That's not to say that these can't be massive and cause a tremendous amount of damage, but it means that the earthquakes are not coming from very, very deep within the earth, as opposed to our two convergent boundary cases, subduction and continental collision. Notice we have blue earthquakes running down sometimes tens or even hundreds of kilometers into the surface. Sometimes it's helpful to think of this in the reverse process. Rather than saying, okay, we know this is a subducting plate boundary, so we should have deep earthquakes. Well, the earthquakes are something that we would notice first, and we work backwards from that. So first we notice, wow, there are these really deep earthquakes in this area. Then we say, okay, well, maybe this is either a collision or a subduction boundary. Earthquake basics. So what is going on with an earthquake? This is when we have two discrete blocks of the earth that slip past each other. You can imagine a case where two blocks are being held against each other and a tremendous amount of pressure. The amount of pressure between them builds and builds and builds and builds over time until it ruptures. As it ruptures, you get this tremendous release of energy, producing seismic waves which radiate out in all directions. These are usually located at plate boundaries, but there are no rules for this. Earthquakes can happen anywhere. They can happen in the middle of a plate. They can happen at the plate boundary. They can happen pretty much anywhere on the Earth or in the Earth. The energy radiates outward from them in all directions, sending waves three-dimensionally, radially outward, like ripples in a pond. We call the study of earthquakes and of the waves which the earthquakes produce seismology. So this diagram shows the basic parts of an earthquake. We have a fault surface. This is our discontinuity. This is the surface where the plates are sliding past each other, or where the blocks of earth are sliding past each other, I should say. There is the focal point. This is the origin of the rupture for the earthquake. This is the place where all the energy is released from, going radially outward. And above the focus is the epicenter. This is the expression of the earthquake at the surface. And the distinction here is important. So the focus is three-dimensional. It's where the original rupture happens, which produces the earthquake, where all the energy is released from, as opposed to where that energy reaches the surface directly above the focus. This is the epicenter. We see also with earthquakes a tremendous amount of aftershocks. So a big earthquake has an initial largest release of energy, but you can see actually in this case a fairly sizable earthquake, a 7.5, we'll talk about more about what that means in a bit, released energy not just once, but over the course of an entire year. Many, many smaller earthquakes as the fault continues to shift into a more stable position and releases energy in steps along the way. This is a map of the US. As you would expect, most of the seismic activity is concentrated here on the west coast. There's also a tremendous amount here in Alaska along the Aleutian Arc. But there's something else here which should jump out at you if you take a moment. It's going to be here in the middle of the continent. So earthquakes, even though they tend to happen at these plate boundaries, can happen anywhere, including in the middle of a continent. What's happening here is you have a very, very old fault in the basement, deep, deep within the earth. Something which is an ancient structure that, for whatever reason, is still active and still producing earthquakes today, despite being far away from the plate boundary. You also notice here in Oklahoma, this is induced. Many of you, I'm sure, are familiar with hydraulic fracturing or fracking. The waste products of this include a tremendous amount of wastewater, which we can't use for anything else. What has happened here in Oklahoma is that this wastewater has been injected deep, deep, deep into the ground. So much water has been injected so deep into the ground that it is causing a reactivation of structures which are down there. This is completely induced by human activities in Oklahoma. So this is our global seismic hazard map. As you would imagine, most of it is concentrated here along the west coast of North and South America. There's also a tremendous amount running here from the Mediterranean through the Middle East all the way over to the Himalayas, as well as some here on the east coast of Asia. And a diagram like this, you can imagine a distant past where plate tectonics had not been settled. We weren't sure exactly what was causing things. Instead, all we have is this map of things which anybody could observe at the surface. This is where earthquakes happen. Well, it definitely looks like there's this discrete mass over here which is causing all of these earthquakes. You can see from looking at a map like this of earthquake activity how somebody could come up with plate tectonics despite having no geological basis for it. Instead, they could just see, well, look, it just seems apparent that the Earth is subdivided into these individual plates. And that, more than likely, activity is going to be concentrated on the edge of these plates where they bump into one another. Talk about earthquake zones. So from the last map, you might have seen most of this is concentrated along the outer edges of the Pacific Plate. A substantial minority, about 17%, is through the Alpine Himalayan seismic belt. There's everything from the Alps and the Mediterranean running all the way through the Himalayas. There is a little bit scattered in various areas around the world, about 2% of it, despite how seismically active certain areas like Los Angeles or Alaska may seem. And finally, Indonesia seems to be the global hotspot for earthquakes. If you want to take a moment here, there's that same map shifted over to try to identify where Indonesia is. Of course, it's right there. So, coming to Arizona, and you might want to pause your video here and think for a moment, what do you think would be the most earthquake-prone area in Arizona? As it would turn out, Arizona is divided into two regimes, you could say. One down here, as you may recall, which is under extension, basin and range, and one up here, which is not, where we see the seismic activity concentrated. Again, even if somebody knew nothing about geology, geology was not a science, not invented yet, if they had a map of where people were reporting earthquakes, something like this, they might be able to guess, well, it looks like there's a lot of them up here. This is its own geologic region, and not very many down here at all. This must be two different zones of geologic activity. Next section will be on the types of faults.